guys, I'm Mick and I'm here to talk to you about service levels in the world of SOA. So, who am I? I am a senior engineer at Reliably. We build various things around service levels, tooling to build them, information about how they're good, suggestions about how to improve them, and a whole bunch of extra value-added things that tell you useful information about how to manage your service levels over time. I'm based in the UK, but thanks to COVID-19, I now work anywhere, anywhen, all from this very room. What a time to be alive. I've been in tech for 12 years. I've been a dev, I've worked in ops, and I've also worked in product management. What I can say is that service levels actually impact all three of these things, although it can be a little bit invisible as to how that happens, but it always has an impact. And for a humanizing fact, I was once chased up a tree by a cow. Cow tipping is not the victimless crime you think it would be. That's all I'm going to say. So it's kind of hard to talk about service levels without first going into the terms. I realize that I might be teaching a few people to suck eggs here, so forgive me, but we'll just run over it quickly. So the big one at the top that we see when we work with cloud providers, for instance, is the SLA, which is effectively a legal mechanism that you have to demand some form of compensation if a particular provider doesn't give the experience you expect. They oftentimes exist, but they tend to require a level of corporate level agreement between two systems, between two parties, and that is not always forthcoming. SLOs, however, are something that pretty much every service has got, even if they don't have one codified. A team will often want to have a known measure of good, an objective that says how well their service is performing or not performing. An SLI is the thing they use to measure that. So if you have an objective which says 99% of requests should occur or be handled in completion in 200 milliseconds, the measurement would be how many milliseconds do it on average does a request take. So SLIs feed SLOs. An interesting part to add to that is that a service level applies to any system that has a user, not even technical systems, but any system at all. If you go to a post office, there's a service level there for how long it will take you to get your parcel given over there and then sent to the destination. Most providers say 2 days. That's fair. There's not an SLA there, it's an SLO. There's no real recourse if they don't perform. It's kind of an implicit agreement. In services, it can be more explicit or more implicit. It doesn't really matter. It depends on your service. But any system where system meets the meat, that's where the service level lives. So, where's the connection to SOAs? The important thing that's come out in the last 10 years, pretty much with the dawn of smartphones, if you really think about it, the world of modern tech is basically a bowl of service spaghetti. Services are everywhere. Web services, REST services. Most systems now come with a REST interface of some sort, or at least an API of some sort, which is designed to be consumed by anyone, not necessarily by the systems just built and operated by that particular company. An important matter that needs to be expressed is that any system that depends on another system, it becomes beholden to that system's service level. So if you offer 3 nines of availability, but you connect to or you directly depend upon a system that only provides 2 nines, realistically, you cannot offer a better service level than the service level of the thing you're depending upon. There are some edge cases to that. It's not as clear, straightforward as that, and I'll go into the ins and outs. But basically, that's an important thing to think about at all times, that by connecting to a service, you are now beholden on that service being there for you to do your work. So, a mathematical model, and there is a mathematical model behind the way we can figure this stuff out. This is something we've built reliably, and it underpins a little bit of what we do. So effectively, the top formula you're seeing is the big one. It's it's the one that describes everything, but we have to define it a little bit more and expand upon it to make it make sense. So the aggregate service level is effectively the minimum service level you're likely to provide. Not necessarily the same as an agreement. An agreement should probably still be even tighter still to give you a bit of wiggle room. Eventually, you will not always meet your service level. A is the service level of the bit you have built, the bit you are directly responsible for. So it could be a Lambda function with DynamoDB behind it. You might say that I can engineer this in such a way that it has 3 nines of availability. Excellent. B is the product of the service level agreements of all services you depend upon. Now, this is a difficult number to figure out, and this equation becomes complex the more you add to it. This is the basic numbers. It gives you a good idea to get started. If you use reliably, we can help you further expand upon that by showing you some of the interesting sections that come into this to further refine this to understand where your weak points are likely to be. Let's do an example. So assume you have a service that has an SLO of 99.5, 2.5 nines, and you depend on 2 services that have an SLA, not an SLO, an SLA of 99.95 and 99% respectively. In this case, N equals 0.995 times the product of 0.9995 and 0.99. Luckily, I've worked this out for you, so no one has to do it in your head. It's 98.46%. So even though your objective is 99.5%, you're over 1 full percentage point lower in expectation simply because you have dependencies that are always going to impact you. You're always going to be affected by them. As I mentioned, it's not that simple. Most systems at the minute are microservices are quite a sexy term, although they're kind of falling out of favor to well-architected monoliths, so it's a difficult one, this. What you can generally say is that there is never really going to be one single path through a system. If there was, then the equation you just saw would work every single time, since there is no possible way to branch into a different code path where a dependency wouldn't apply. Assuming that your dependencies apply to every single code path through your system, the previous example will work every single time and give you a very stable number. But it's just not the case in the real world. In the real world, you might find that only 2% of your traffic actually uses a particular service. So the fact that that service has a phenomenally high success rate actually doesn't affect you very much at all. You could have used maybe a cheaper tier of that service, or you could have used a different service altogether that offers similar functionality but costs less. It's an interesting concept. It's something that comes up quite a lot in service levels beyond just the technical notion of how. It comes into what and why. It's also possible to engineer resiliency, and I'll go into that a little bit, how we can architect a solution to some of these problems. And also, not all dependencies are equal. Some dependencies are critical. A great one to point out there is authentication level dependencies. They tend to be quite cross-cutting. But some dependencies, for instance, logging dependencies, you may not need them to be there every single time, especially if you've got a fairly robust system like Watson, or maybe even something like FluentD, which is able to pick this stuff up after it happens. It doesn't have to be happening in real time in a synchronous fashion, in which case the dependency is there, but its impact is actually greatly reduced. Its blast radius is greatly contained. So, what can we do to architect a better SLO? We can actually modify the architecture of our application to better handle systems where services are up and down. Transient errors are a great example where this is a very, very easy win. It's a cheap optimization. Frankly, you should always do it. Imagine you've got a system that has 3 nines and it depends upon a service that has 2 nines. So every single request that goes through that system has that level of uptime, which means you're 98.9%, which is okay. Maybe not enough though. But if you introduce a simple retry mechanism, every time that fails, say it's 3 retries, whenever that fails, you've got another bite of the cherry and then another bite of the cherry again, just on the off chance. That effectively means that if a transient error comes up, your uptime has been increased by 99 to 99.6%. We're suddenly above the 2.5 nines. As I mentioned, web services are brilliant for this kind of thing because they have a status code baked in, which basically lets you know that the error that's happening is transient. So here's a 503, guys. Try again later. There are some restrictions in a synchronous system, obviously. Most HTTP systems only provide a 30-second window. Some provide less. You need to kind of understand what likely timeout you're going to be getting and then work within it. You don't really want to be doing that third retry just past the point when the client has stopped listening for a response. You need to be aware of it. This is purely arbitrary and it's my opinion, but I tend to go on 15 seconds maximum. So the maximum amount of time I want to spend is 15 seconds. It is also worth mentioning that this becomes much more difficult if you have several service calls happening sequentially. So if the first one fails and requires that retry up to 15 seconds, and you want the entire request to only take 15 seconds, you've eaten all that time early. There's a nice function in Lambda that lets you understand how much remaining time is left in an invocation. If you don't use Lambda, you can still introduce that same concept at the request level. And that's crazy powerful, something that you should definitely look at doing if you write a web service of any sort. And if you do write web services, I can't say it enough, send the right status code. 500 is fine, but it also simply says that it's dead. Doesn't really give much more context than that. If it's transient and you send a 503, you're at least giving intent to your client to say, you should probably retry this later, which could be a few seconds from now. There's a lot of value in that. Transactional errors are a bit more of a beast. They're difficult to architect around because effectively if you have a transaction lock or you have transactions that have failed, your only chance is to roll them back and let your user retry them from the start. And if the same circumstances exist that caused the failure in the first case, the failure in the second case is likely to be the same problem. What you can do, though, is actually break your transactions down and become what's known as transactionally transparent. What this means is that instead of a user directly saying, here's a change to my record, go make it, what they can do instead is say, I'd like to make a change to my record. It goes up to your service puts it in a queue of some form, time passes, and then a handler takes that request off the queue and does the work. If it fails, it lets the user know. If it doesn't fail, then it can put it back on the queue. Let it keep going round until it can actually succeed successfully or it times out. Either way, we provide an inform user step at the end. Basically, this is event-driven architecture 101. It's crazy powerful, but it does change the user experience, and it definitely works against the concept of HTTP, where you get a valuable response immediately, especially if it's something like a post. A put isn't so bad, but a post is tricky because the HTTP spec says that you should always provide a location for the new entity. You can get around that by actually creating the entity record and then leaving it blank or adding a message in there which lets the person know the current state of the entity. So there are ways around it, but it does involve thinking up front what will happen when inevitably these things fail. Luckily, if you don't want to go that far, you just want to add the simple sort of event bus plus webhook. Lots of that stuff already out there. People are very, very comfortable with it. In fact, if you've done much with GitHub, webhooks are pretty much the bread and butter for that kind of thing. Very, very powerful. One thing I do want to add at the bottom of this one is if you're writing a system that has transactions and potentially has transaction failures, avoid distributed transactions absolutely wherever possible. They're no good can come from using a distributed transaction. It'll steal your money, run away with your wife, burn your house down, and kill your pets. They are hateful things. And unless your actual business model is to provide distributed transactions, such as Google with their Chubby service, it's just not worth the effort. It's better to take a step back, find the distributed the transaction boundary, and wrap a component that size. It will make your life so much easier in the long run. One that you can't really not talk about, if you're talking about architecting this stuff, is caching. It is completely fair to say the two hardest things in software engineering are naming things and cache exploration. Caching is a bear. It is. But it also offers an incredible capability when it comes to service levels. The absolute best way to minimize the impact of a service on your service is to not make the call. Simple as that. Again, HTTP provides us with a lot of mechanisms, especially the spec now, but it's been in there forever, for cache control. If you make a read and you have a cache control header returned to you, cache the information as the cache control header suggests. Do it every time. Because if you can prevent yourself having to make that call, then you straight away take any notion that you have to be beholden to that service level. And on the flip side, if you produce information that is consumed and it is read by your users, don't feel that you can't cache it. Understand your service, understand the usage, understand the consistency of the data so that you can actually provide a decent cache control mechanism. It might be that you could even go just as simple as saying, you can cache this for 5 minutes. It might not be that much, but you tend to find that in a lot of cases, requests are made quite bursty. So a single item might have many calls to try and understand what's going on with it. If you're able to cache that stuff, then it's much more powerful. So this is a bit of a wrap up now, and I realise that I've dusted over something quite quickly there. So by all means, come and see us at Reliably, and we'll talk this stuff through even deeper. It's such a deep and rich topic. But basically, in a networked world, there's no service level that stands alone. Not one. Everything impacts everything else. Think about the last time Facebook went down and the world caught on fire. People were going ballistic. That's the world we live in today. Expect everything at the touch of a button. You need to be able to offer the best possible experience for that. If you're building services, build them in a way that gives your users the best opportunity to use the service well. That means taking advantage of the fact that a lot of the information you need to convey to users already exists in the HTTP spec. Not everyone uses it properly. Consumers might not, but if you've offered it in the right way, then you've at least given them the best opportunity to use it well. If you go even further and start documenting this stuff well, then you're taking the extra step of ensuring that your service level doesn't impact them as badly as it could, because eventually you will have downtime, which kind of gets to the last point here. Don't be afraid of downtime. You simply can't be up all the time. It's not possible. It's not even practical. And it's precipitatively expensive to try. It is possible to build a system that has many, many layers of resilience, but what you tend to find at some point is that the resilience starts being offset by the cost of the complexity. So while you're able to be incredibly resilient on one side, the amount of change and amount of value you can add minimizes because the thing is so complex, it's hard to change. It's a horrible double-edged sword, but it's just the nature of the beast. So yeah, try and strike that nice balance, that trade-off wherever you can. And that's it, guys. Thank you all very much for listening. And come and see us at Reliably. We're building some brilliant stuff. It's very early days for us, but come talk to us. We've got some interesting ideas and we want to see how our stuff works in the real world. Thank you very much.